Josh, please take it away.
Thanks. Good point. This could potentially replace some products you're going to see at RSA this week. So thanks everyone for coming to my talk, and thanks to the organizers for inviting me to speak. This talk's focused on tools and techniques you can use to identify and detect malicious files in your enterprise. The first third of the talk is going to be an overview of detection-oriented file analysis, while the last 2/3 will be a bit more technical. We'll end up walking through a real-world example of detecting malicious attributes in a document file. So before I jump into the details, I just wanted to quickly highlight my background. I've been working in threat detection for 6 years. I currently work at Target. I'm a lead engineer in their Cyber Fusion Center, and you can find me all over the various social sites with my handle right there. Also, I work from home, so I wanted to give a shout out to my perennial coworkers of the year over here on the right. So my talk today really is to try to convince you to consider adding detection-oriented file analysis to your threat detection program, because it resolves a data visibility gap that goes unaddressed by tools like antivirus and malware sandboxes, and it's a data visibility gap that you definitely or probably have. To start, sometimes it's helpful to look at a definition. I consider this kind of file analysis to be any that enables real-time threat detection through enrichment, extraction, and metadata collection. The goal of a system that does this kind of analysis is to collect enough data to allow defenders to either automatically or manually identify adversaries in their network. So systems that do this have two defining traits to me. First, they generate a lot of file metadata from which you derive insight. And second, they are or should be relatively easy to integrate with the detection systems you currently have, while also being customizable to your needs. So definitions are nice, but the real question is, what's in it for you if you decide to use a system like this? So the important thing to keep in mind about what I'm going to describe next is that these systems need to do all of their tasks quickly and at scale in order to support real-time detection in a large enterprise. So first, these kind of systems provide a pretty comprehensive level of detail across all kinds of files, and that's important so defenders always have a consistent data set to work from. This includes most commonly performing simple tasks like hashing every file with MD5 or SHA-256. Next, these systems commonly perform recursive file analysis. That is, they extract files from within other files and submit them to the analysis engine for processing. You might normally think that this only applies to something like archive files, but it also equally applies to documents, images, even text files can contain other files. And it's important that all those files are supported. And finally, there are just some files that you see in your enterprise that are more interesting than others, and those always tend to get special treatment in these kinds of systems. This would include something like targeting a specific type of metadata that's used to identify adversary activity. For example, doing verbose data collection of an executable's import address table could be important to you. That kind of idea, having file-specific metadata inspection, applies to dozens and dozens of kinds of files. So what's especially interesting to me about this kind of analysis is that it's really very underused in the active threat detection space. There aren't a lot of organizations who are doing this despite it being highly valuable. This is a release timeline of systems that people commonly reference when they talk about doing this kind of file analysis. The main thing I want to point out about this list is that these systems share common design patterns, but they have different intended purposes. The three I've highlighted here are commonly used as detection and intelligence gathering systems, while some of the others are more focused on scanning malware or automating mundane analyst tasks. So in this presentation, I'll be talking about Strelka, which is the project that I open sourced under Target last year. But if any of what I say today piques your interest, I'd suggest you take this list, review the projects on it, and see which ones may best fit your requirements and use cases. So now we'll talk about Strelka. If you're not familiar with her, she's one of the second-generation Soviet space dogs to achieve orbital flight. And the project is named as such because it borrows the system architecture from Lockheed Martin's Leica project. So when it came time to name this project, I wanted to pay homage to their work through the name. This system can be simplest described as a recursive static file analysis system that's built on Python and 0MQ. One of the most significant changes we've made to this project compared to some of the other ones that were shown earlier is that we don't support Python 2. When it came time to start thinking about what the design of a new system like this would be, I knew Python 2 couldn't be supported because its end of life is supposedly coming up very soon next year. So out of the box, Strelka will produce event data for over 60 unique kinds of files. And we place a pretty significant focus on files that are likely to be used for malicious purposes. Normally, you might think of documents and executables as files that are likely to be used maliciously, but something like HTML could be just as malicious as an executable given the right context. This project has what I think are a number of unique features. Many of them are described on the GitHub page for it. Some of my favorites that are real differentiators are the focus on scanning text-based files. I mentioned HTML. We also support XML, Visual Basic Code, JavaScript, Batch script, many more. And the project is heavily focused on language-neutral components. So we use 0MQ for networking. We use protobuf for the messaging format. We use YAML for the configuration files. The project core is written in Python, but technically you could write portions of it in nearly any language you want that is supported by those components. So here we have a system architecture diagram of Strelka. The two important things that I immediately call out here are the dotted lines running north to south. Those are network hops, so this is a distributed system. And the second thing is the components in the center. So those two components constitute a cluster. Now, from a deployment point of view, Strelka's primary goal is to integrate with whatever existing systems you have for detection as seamlessly as possible. On the front end, that means that clients tend to be things like network security monitoring sensors, and that they just continuously push files to the cluster. On the back end, the event data is written in JSON, and you really can do whatever you want with it. Most users end up sending it to a centralized log aggregation system like Splunk or Elastic. You could also just stick it in an on-prem or cloud database. We don't limit what you can do with the data. We just make it available to you. What is cool about that system architecture is that it makes it really easy to scale a cluster. So the cluster I manage regularly scans up to 150 million files a day, which is also approximately 3 terabytes of file content a day. And the system will keep track of how long it takes to scan each file. So for the cluster I manage, at the 95th percentile, it takes 13 to 14 seconds to scan a file. As soon as you go to the 85th percentile and lower, you hit sub-second scan times. So the speed of an individual scan plus the distributed design really means you can scale to whatever volume of files you need to handle. When I introduce this project to people for the first time, there's always some questions that pop up right away, and these are those questions. I don't consider this to be an intrusion detection system. I say that it enables intrusion detection. You still need a human to decide what to do with the data that gets produced. That could be writing automated alerts from the data or manually crawling through the data via something like threat hunting. It's written in Python because Python has good third-party package support for the kinds of files we care to scan, and it really is just good enough. The system architecture lets us bypass any inefficiencies it has through brute force scaling. And when it comes to scalability, we don't use microservices because they're way too difficult to manage and really are overkill for the vast majority of users. We use cookie cutter scaling, which means you build a cluster. If it hasn't met the scale you need, you just keep adding carbon copies of the same server to the cluster until you either hit the scale you need or you run out of hardware. So those are really the introductory details. This is where we kind of get to the interesting part of this talk, which is what you can actually find with this data. And to do that, what I'm going to do is call on someone I follow on Twitter. So this is John Lambert. He works over at Microsoft. And he shares a lot of interesting malware samples online, many of which, unsurprisingly, include Office documents. What we're going to do here is take one of the samples he shared late last summer, walk through the Strelka data for that file, and try to determine if we think it's malicious or not. So what we'll be looking at are 3 files in total. The first file is an Office document. It's a resume from Amanda. And the second 2 files are files that are nested inside of that document. And while we do this, I just would like you to remember this stat that's over here on the left. Only 6 out of 59 AV engines flagged this document as suspicious, which is a pretty low percentage, less than, well, approximately 10%. So this is the literal JSON output of the Strelka engine or system. This is file 1 of 3 that we'll be looking at. This is the document itself. Before we really dig in here, I think it's important to call out some of the structure of the data. The first is that at the root of the JSON event, there's a variety of metadata dictionaries. And they're all very literally named for the data that is encapsulated within them. So hash metadata is the result of hashing functions. Zip metadata is artifacts related to zip extraction. XFTool metadata is related to the output of the XFTool utility, things like that. These are very literally named, so it's easy for an analyst to understand what the data represents. The thing that is a little weirder and not literally named is this thing called flavors at the top. So in Strelka, we don't identify files by type, we identify them by flavor. And that's because sometimes it's useful to identify a file by more than its type. An example of that would be, say you have an XML file that is simultaneously a malware configuration file. Those are both valid ways to identify that file. And we use these flavors to assign scanners that produce the metadata you see here. So it's important that we're flexible in how we name these things. The 2 primary methods of tasting flavors in the system is through libmagic and Yara, represented by the MIME and Yara fields in the flavors dictionary. So what we're actually going to do here is we're going to walk through this almost line by line, and I'll talk to the interesting points here. First, if we didn't already know that this was an Office document, the flavors are the thing that tell us that it is. This happens to be a docx file. That's what it would normally appear to be on an endpoint if you were looking at the file. That's a Office open XML file. The other interesting thing about the system is that we hash every file no matter what, so it always gets MD5, SHA-1, SHA-256, et cetera. We also assign a unique ID to the file because you need to be able to keep track of files that are directly related to one another. So we tag it with this unique ID. If you keep an eye on the value of that UID, you'll see it pop up here again momentarily. Now, this is where we actually kind of get into the interesting bits of detecting adversaries when we look at the XFTool metadata for this document. The interesting so if you're not familiar with XFTool, it's a fairly popular utility to parse generic metadata out of a variety of files, hundreds of files, documents, image files, archive files, many kinds. What is interesting about this set of metadata for this document is that there's nothing interesting about it. You can see from the word count that the document appears to have a reasonable amount of words in it. It's got basically a reasonable amount of content for a resume. Creator value contains Amanda's name, which matches the resume content. You could actually go back and look at John's tweet to confirm that. So what's interesting about this being uninteresting is that it isn't uncommon for adversaries to flub the values of this metadata. For example, they might do something like send you a resume that has 5 words in it, which is weird, or send you a resume that has a creator value that is just a random string and not someone's name. Those are interesting things that you could use as detection breadcrumbs to figure out if you're dealing with something that might be malicious. So that's really all there is to that. This is going to kind of come into play later. What's interesting is that the adversary in this case did a pretty good job of trying to, obfuscate their delivery of malware, but it ends up being pretty futile in the end. The last point here is that these files, they have the structure of a zip. So that means that when they are introduced to the system, they get extracted as if they were a zip file. So we just take all 18 parts out of the file and parse those out, and that's what we're going to be looking at here next, is one of those 18 files. I believe this document has 18 parts in all. So this is the second file, 2 of 3, And the thing to call out here is the existence of this dictionary called VBA metadata. That's Visual Basic Application Metadata. That's basically the thing in this metadata that tells you this document might have macros in it. Macros being, the thing that is intended to help end users by automating document-related tasks, but is typically used by adversaries to automate the installation of malware. So if you look at the flavors, there's really nothing too interesting here. This is identified as an OLE compound file, which you actually don't need to know too much about. It's just a kind of file that stores other files. And in documents, it commonly stores macros. Once again, we hash all the files. We assign a unique ID to all the files. In this case, there's a new field. It's called parent UID. It contains the value of the UID from the previous file. So this is how we very explicitly relate files together. It's important if you're looking at this kind of data to be able to pivot between files that are related. And finally, the VBA metadata actually doesn't say too much that's interesting, except it confirms any suspicions we had that, yes, there was macro code inside the document. And we're going to be looking at the actual code of one of the macros here in the next slide. The VBA scanner also tries to be helpful and tell you about suspicious things in the VBA code, like base64 encoded content. We're going to look at that more in depth here in the next file. So this is the third file. It's 3 of 3. This is the Visual Basic code from one of the macros. This is nested pretty deep within the document. And what's interesting is that nearly everything that's detection worthy about this entire document, all 30 plus parts, can be found in one field here, which is the VB metadata strings. So these are literally strings defined in the VB code as like variable definitions, right? Like A equals blah. That's the kind of string we're talking about here. We're going to spend pretty much the rest of the presentation on that in particular because there's just so much to unpack there. If you look at the flavors, Yara successfully identifies this as VB code. LibMagic has no idea what VB code is, so it just says it's plain text, which is correct, though a little inaccurate. I'll skip the hash metadata and UID. Once again, we hash everything all the time, and this is how you relate files together. But the VB strings is really where things kind of pop off here in this document. The first thing that's interesting is this Python one-liner. And as I'm going through this, I want you to just recall, this is a resume from Amanda. Why does it have a macro that contains, a Python one-liner that is base64 decoding a very long string? In this case, the string was so long, I had to truncate it for space. Otherwise, all of this would have been illegible. There's also something else that's interesting here, which is that they explicitly call a function to filter out and ignore any warnings thrown by the Python interpreter. I'll kind of leave you to think about that for a minute. We'll come back to that at the end here, why they may want to do that. So that's weird that exists at all in someone's resume. But then it gets even weirder when you see this reference at the end of the first highlighted line here to a launch agents directory and a Spotify browser API property list file. So this is really your first indicator that you're looking at something that's targeting a Mac user and not a Windows user. If you're not familiar with launch agents or property lists, they're used to control system-level processes on a Mac. What's even more interesting is that not only do they reference the file, they actually have the actual structure of a property list file that follows it. So you can see on the second line here, there's the header of a plist file. At the end of the third line, there is a label that gets set that says Spotify browser API. Which is clever. So they seem to be, from what I can tell, I'm not doing forensics here, I'm just looking at metadata, so we're making some guesses. It appears what's probably happening is that they are inserting the content into that file location, right? So they're either creating or overwriting that Spotify browser API plist. But it goes even further because they actually define, this is all non-encoded data, this is just plain text in the VB code. They go even further and they define what program is executed by the plist. And what they have here is they have an array that says Python, TAC-C, and then a blank string space. And so we can't prove what is included, what Python is actually executing here, right? But a pretty good theory is that it's the one-liner we saw earlier in the VB code, right? They could assign that, they could insert that into the plist via a variable definition, which is very likely what's happening here. And so if we're right, what that means is, it means that when the plist initializes and runs on the system, it's actually executing whatever that Python blob is. So we can actually go even further. It really gets crazier. The plist attributes there are attributes that really kind of clue you into adversarial intent and how they're attempting to maintain control over the system. Here, the run at load key means run the program when the system boots. The start interval and keep alive keys are methods of ensuring that the program is always running. So these are methods of persistence for processes that are controlled by a property list file. This guarantees that that Python one-liner is always running. The last thing here is this curl command, and there's a lot to unpack just even in this one bit of the VB code. But in this curl command, they do some interesting things. So the first thing they do is they override curl's default user agent string, and they set it to mimic a MAC, which is pretty clever. So that's the first indicator. Like if you don't know anything about launch agents orplists or how the Mac OS works, that's your thing that tells you like this is certainly targeting a Mac user. But they go even further, and they actually suppress the output of curl, which is a fun callback to the technique they use in the Python one-liner to suppress warnings. So Python and curl have these portions built into their code to suppress output, essentially, right? And that's an advantage for the adversary because it means when they execute code in your environment that you're less likely to see them. The other two things that are interesting about this are the domain that's used. So a very attentive analyst or say a domain reputation service that is keyed into that domain would eventually be able to tell you that it is not a legitimate Spotify domain. And then finally, they're not downloading data from this domain, they're uploading data to it. So the TACD flag says that. So once again, we're not doing forensics, we're just looking at metadata, so I can't authoritatively tell you what they're uploading. But what's suspicious is that immediately after that, there's a definition or a variable assignment for a shell command substitution, which contains the system's host name and current user. Which, if you think about it, makes a lot of sense because when an adversary gains access to your network, what kinds of things do they need to know? They need to know where they landed in the network, which you could glean from a host name, and they need to know what level of access they have to the network, which you could glean from, the current user that is running on the system you've just popped. Now, if you're not familiar with MITRE's attack matrix, which it's actually been mentioned a lot during this conference, so maybe you are now, what I've done is I've mapped the techniques I just walked through to the attack matrix, the tactics on the right, the techniques I just walked through on the left. And I think, so one thing I want to stress about all these techniques, I'm not going to read them because we just literally went through them, but these techniques individually may or may not be detection worthy on their own, but in aggregate, they create what I think is a pretty compelling argument for a file analysis system like Strelka and its use in detecting adversaries. So remember, this document had a low antivirus detection rate. Malware sandboxes are not designed to collect this kind of data and make it easily available at large scale. And in addition to all of that, adversaries don't really expect you to have this level of insight into the files that are moving in, out, and around your network. Because if they did, this adversary probably wouldn't have left all that data unencoded. So that's kind of where I'll wrap it up. Once again, what I'd like to say about this is that if any of it piques your interest, I'd be happy to chat with you about this project or point you in the direction of project owners for any of the other projects that were shared earlier. I think if you're interested in maturing your threat detection program, I'd recommend you take a look at this kind of file analysis because it opens up levels of insight that adversaries really don't expect you to have. And that gives you a pretty big advantage when they try to jump into your network. I consider this kind of data to be fifth tentpole in the commonly thought of tentpoles of threat detection being network data, endpoint data, cloud data, authentication data. I think file data like this could easily become a significant part of a threat detection program. And that's really where I'll leave it to any questions that came in online or in the room.
We have a question from Ron. You stated 6 out of 59 AV engines marked the files as malicious. Which AV engines were those?
Yeah, that's an interesting question. I actually happened to look that up right before this talk. And it wasn't any engines you're probably running. It's stuff like Sentinel-1, not to call out vendors or anything like that. I'm not recommending vendors here, but it was vendors that are more geared toward behavioral analysis and not signature analysis. None of your top 5 AV vendors detected this.
Great work. As someone who does file detection, I had a couple of follow-up questions. Do you guys, does Strelka handle packed extraction of features from packed files or obfuscated file samples?
Well, so what's interesting about it, I don't know that it does out of the box. So we have support for, let me jump back here. So these are the 5 main categories we support, but it's all just Python code. So you could very easily write your own scanning code to handle whatever kind of file you like. And then the way it works is you write a complementary Yara signature to identify the file generically.
Right.
Yeah.
Okay. So this is plugin friendly, and you could add your own plugins
Yes.
like Stoke or like a boss does.
Absolutely, yeah.
Okay,
It's designed to be very easy to add your own code to it.
Perfect.
Yeah.
And when you scan, like in the sample, you scanned 18 levels of associated files. What's the limit? Have you had a zip bomb or an archive bomb like that happen?
So there's a lot of nuance built into this that I really don't have time to go through. But yes, zip bombs are a threat to systems like this. So all of the scanners that extract files, they do have file limits. The default limit is very high, like 1,000 files, things like that. In the case of a zip bomb, you're more likely to run out of memory before you actually hit that file limit. So you do need to just do like system hygiene, system hardening to protect yourself against files that might be actively trying to mess with systems like this. Yeah, thanks.
First, thanks for the presentation. Awesome stuff. Couple questions about what the project supports, if that's okay.
Yep.
So when you're doing VBA extraction, are you relying on external libraries like OLE tools, or are you doing something custom?
OLE tools. So one thing I didn't really talk about is this project is all pretty much my work. So we don't have a team supporting this. It's just what I do in my equivalent of like 10% time. So it's heavily reliant on third-party packages.
Cool. And this kind of bleeds into the previous question. How difficult would it be to expand analysis like pipeline? So if I wanted to treat the OOXML file as like a straight zip and look at timestamps within the file, is that something that...
Yeah, it's very easy. I mean, as long as you have written code in Python before, it's all very easy to do. The README is absurdly long and very detailed to help you with that.
Cool. And have you looked at RSIDs in RTFs or OOXML files?
Not specifically, no.
Cool. Thank you.
Yep.
One last question. Do we have anyone? Yes, we do, in the far back, way up near the top of Mount Everest.
So I kind of tricked you. It's actually a statement, not a question. First of all, thanks for your talk. Thanks for your contribution. And this is being recorded, right? Yeah. Your boss should totally give you a raise. Well done.
Thank you.
Thank you, Josh. It's been a pleasure.
Thanks. Thanks, everyone.